indicator.
So Eric, tell us what's going on here.
We're transmitting.
So this is the Telluric transmitter. Transmitter's inside on the bench, and 1.999 megacycle?
Kilocycles.
1999 kilocycles. Configured as a beacon for a long-term Telluric test platform.
So is this Morse code, or what?
Yeah.
What is?
Yes, Morse code.
Okay, so what is? Can you translate what is flashing?
Just my call letters and identifier. That it's just test transmission.
Yeah. So it's ready for somebody to pick up if they have
Right
a
now.
receiver tuned to it right now,
I'm
right?
just gonna. This is finished. I'm just gonna leave it on.
Yeah.
I'll turn it off when it's raining.
It's the little things.
Right.
Yeah, you can just leave a tube out here, and somebody will just think you got a problem with your neon sign.
Well, I don't want to be attracting a lot of attention, but what I do want to do is I want to have a little bracket with, like one of those little skinny fluorescent tubes. Something that's not really,
Conspicuous.
obvious, but indicates, something that indicates activity.
Yeah.
Yeah.
Plus, this is robbing power. The TCS, will be a lot weaker. It's only going to be half the power of this, at least to start with, until the power supply is built for it.
Yeah.
Okay, we're out here at the platform with the transmitter coil for the Telluric transmission project.
So this is basically the finalized beacon transmitter. It's going to be operating on my ham radio license on a frequency of 1999 kilocycles per second. So this is a scale model that Griffin Brock built of the Alexanderson series coil at the Bolinas KET station in Bolinas. So it's been sized so as to work around 2 megacycles per second of frequency. So at any rate, this connects to, there's a massive tank here, somewhere over 20 or 30 gallons underneath us, filled with water that serves as the ground electrode. You can see the cover for it down there, and the earth connections going into it. And then the elevated capacity, that kind of fine tunes the thing, so it was not easy to get this thing tuned up. So we had worked a couple of days to get this thing on frequency. It's very small changes in capacitance, and because this thing has to operate in the weather, we can't have like tuning capacitors or any of that kind of stuff. It's got to be all weather tight. So what we did for the tuning capacitors, we took a piece of cable TV coax and connected one end to the outer conductor and the lower end to the inner conductor, and then trimmed the size of that, and that was the tuning capacitor. And we're within probably about 1,000 cycles. So we still got to do the fine tuning yet. And then there's a tuning network that has to go underneath that's not there yet to make the impedance of this thing presentable to, there's a buried coax. I'll probably come over to this box here. So that comes up into this can, and then where we can see it here, here's the transmission line that takes it over to the this appears to be what's taking it over to the Tesla transmitter. And then there's a transformer box underneath. don't know if you can get that or not. That's what's got to be replaced with an antenna tuner. Because the situation here, because we're transmitting in the ground is hot, so we can't ground our equipment or our coax shields to this. So that requires an isolation transformer. But that eventually is going to become a more advanced network, because right now this thing doesn't mate well with the transmitter. But it is operable. Then over here is a sensing electrode. That basically is just like a capacitor facing this, and then that connects to the field strength meter inside next to the transmitter, so that we know how strong this thing is resonating. And that connects to a little BNC connector on the cam, so we can have other test equipment out here. This strap here is going to become a one-term loop, and we cut at this point, and then the connector can go here, and that way we can measure the magnetic field as well, like this measures the electrostatic field. So this basically will become like one big coil, and then another coil's going on here, and that will take the place of the transformer. So there's a lot of evolution here. So we had the thing on the air, but as it always is, when you have anything that uses software, don't expect it to keep working. So the keyer stopped working, and now we're off the air. But at any rate, it was operational, and the keyer will have to be replaced. We'll probably have to go back to the old mechanical ways of doing things, because anything that involves software is very problematic, very unreliable, and we can't have things operating like that. This is all got to operate where you close the doors on the cabinet, it's got to sit there for 10 years and work. You can't have specialists coming in from Geekville to try to figure out what's going on inside. So I deliberately neglected the name that I have for what goes on inside. I'll leave it to your imagination. Yeah, these poles are all wet. It's kind of dampening the whole thing down electrically.
Dragging it.
Yeah. Yeah, these don't have enough aperture. They would have to be up closer. Well, something to fool with another time.
Okay, we got Haka says down here at EPD Labs here in Tonopah, and this is the Telluric transmitter, where the goal is to lock it onto one frequency and have it just constantly transmit, right? Like a beacon for people to be able to pick up. And
so I believe about 2 years ago is when this station first came online for its first test. We basically put everything together, tuned it to whatever it was focusing at, and transmitted from there. What this whole system is basically a ham radio, except it's not the normal ham radio that you would be expecting. So in a normal radio system, you'll have an antenna, and you'll have the antenna, you pump a bunch of energy into the antenna, and it radiates it out into space. And that's normal. The air is the transverse medium, whatever picks it up on the other side. In this station, our antenna is actually the ground. So what this whole system is
and it's like a 15,000 gallon old gas tank or something like that, right?
It was two 20,000 gallon fuel tanks, a very large.
Which is all underneath, which is all under here, because this used to be a dealership. Maybe even a
dealership, something like
yeah.
that. But anyway, instead of a normal antenna where you'd need a very large a normal ham radio where you'd have a very large antenna to radiate a certain frequency, we have a very large ground in order to deliver power into the ground with a higher potential. So what this whole upper system is, this is not meant to radiate out into space. This is meant to be a reflector. So what happens is this Tesla coil, this extra coil, ends up being kind of like a spring. So when we energize it with RF currents from a conventional ham radio, instead of it being emitted through the air, it reflects off here and pumps across the ground. So ideally, we're not emitting anything into space at all. All the energy is getting punched in and out of the ground and being reflected back out. And there's really nobody else that's working on this that we're aware of. The question is essentially, how do the signals propagate? How do these signals compare with conventional aerial signals? Do they travel around the Earth better? Do they have certain daytime, nighttime characteristics? We have some preliminary data from the last 2 years of experiments, but the real question is going to be putting this online as a 24/7 beacon, or at least 12 hours, 24 hours at a time, so that we can have different people listening in across the country and potentially across the planet to see what the propagation characteristics of this are compared to regular ham radio. The difficulty that I've been facing is the whole day tuning this. Our previous test, we basically just banged this entire thing together and ran it at whatever frequency it decided to. Or we had a tuning capacitor we were able to adjust up and down very easily. Because this is meant to be a permanent installation, we can't have an air variable capacitor floating in here where humidity will throw things off, or moisture or anything like that. So essentially our variable capacitor is actually this piece of coax that has to be trimmed to a very specific height in order to have a certain amount of capacitance to bring the system into the resonant frequency that we want. And our goal is to bring it in right on the edge of the 160 meter ham band, which is about 2,000 kilocycles, or just 2 megahertz, just under that as a permanent beacon station. And then a few days, weeks, or months from now, we'll have some data as to what the propagation looks like and see how it acts compared to conventional radio. I'm not sure if there's a whole lot of people that have done this since Tesla, so it's really uncharted territory. We don't know what's possible, what's not possible. But that's where we're at. Hopefully today we'll have something more.
Well, what's the target frequency that people will be able to...
For the hams with the big enough rig listening, the 1999 kilocycles, 1.999 megahertz. And looking forward to it.
For this segment. Okay, so this is the transmitter. So the fluorescent tube that was illuminated that Eric was holding is basically flashing to this Morse code right here sent out by this transmitter. That's the frequency right here. It's live right now, so if you can try to receive that, then send us an email, contact us, and let us know where you are and how far you're picking it up from. This is being sent from Tonopah, Nevada right here, a couple hours northwest of Las Vegas. And this right here will be the...
that's the transceiver that's going to be hooked up.
And you said you need to have a power supply for more power.
Well, it needs some modification. Some of the design functions in there are not really suited for what we're doing, so I have to make a few modifications. And then the dynamotor power supply over there that runs on 12 volts. This thing was only operating at 40 watts, but it's actually a 120 watt transmitter.
Okay.
So when the right power supply is built for it, then these will do what this does without all this digital stuff. These are World War II Navy transmitter receiver pair used on landing craft and PT boats. So it's a real classic. It's been like, in my day, this is like, every ham radio operator when he was a kid had one of these. I did. I've had about 3 or 4 of these. They also have the advantages you can do bootleg on the AM broadcast band with them.
Pirate radio?
Pirate radio. They're great for AM pirate radio. Okay, so this is the transmitter and receiver that's intended to operate with the coil out on the platform. So it's rated for 40 watts, but it will work well at 100 watts without any problems. So Right now it's got a Dynamotor, original Dynamotor power supply that so the thing runs on 12 volts. These were designed to operate on small PT boats and landing ships and landing craft and what have you. So they had to operate off of a 12 volt battery. So these things are extremely reliable, and 40 watts is way underrated. RCA tube manual says that the tubes are capable of 100, so that's what we'll operate at. And then the Dynamotor unit will basically become kind of a terminal box for all the cables and things, so that doesn't have to get changed. And then it's got a terminal strip on it where you can connect an external power supply and not have to use the Dynamotors. So another power supply can be assembled, or there may already be one in a piece of equipment here. I think the radar indicator's got one. And this will be the final transmitter. So this is what we got set up now. So here's the 12 volt system over here. We have the battery charging, and then your normal ham radio. But the automatic keyer that sends out the call letters and other identifying information, that took a squat. You have to program whatever your message is into it, and then it stores that.
And what is the message besides your call sign?
Well, what you do is you start off with the letters QRA, which basically means this is. And then that's followed by the letters DE, which is from, and then my call letters, which is N6KPH, and then there's a break, and then that repeats, and then there's a break, and that repeats, and then after that is the frequency, power, and type of radio, and then a pause, and then the whole thing starts all over again. So that's the way it used to be done in the Morse code days for stations like the one in Bolinas, and all over, actually, all over the whole world, is usually groups of 3. You know, if QRA means this is, 3 Vs means you're testing, and CQ means that you're looking for somebody, you're looking for traffic.
What does QRA come from? What's the acronym? Or
well, there's a whole set of they're called Q codes that were used in the telegraph days, radio telegraph days. It's like QRM means man-made interference, QRN means natural interference, QRT means stop transmission, QSL means that you're asking for a receipt from your transmission. There's a whole set of those. Morse code and radio telegraph in general were filled with all kinds of abbreviations and what have you, because that minimizes the amount of letters you have to send, simplifies a lot of things. So that used to be well known by all the hams in the, in that day, but right now ham radio doesn't.
So radio
do it anymore.
shorthand.
Yeah, radio shorthand. So these are going to have to undergo some modifications, so that's next. And the type of keying they used in these things was really kind of inane, so that has to be modified. All the modifications in this have to be such that it doesn't really affect the overall historical aspect of the equipment. Can't be punching holes in the front panel, or pulling circuits out and swapping shit around, and it's got to be, everything has to be basically just the next modification that would have happened if this radio would have kept going, past World War II. So cathode keying, most of the hams that had these back in my days in the 60s, the first thing you do with this is you change it to cathode keying, because right now it's all these relays turning the plate voltage on and off, and that makes for really lousy sounding code, and you can't go fast, all these relays clicking, and it just doesn't sound good, so you go for cathode keying. And the challenge in that is to try to preserve the AM characteristics, because these things will work for voice, In fact, that's one thing that made them popular back in the day is these are really good for people that lived in the outback. You have one of these sets and you could always communicate with the outside world. It's extremely reliable. The problem with the receiver is that when you're transmitting, it goes completely mute and you can't hear your own signal. And that's really irritating when you're transmitting Morse code and you can't hear your signal. At least for me, it makes it harder to send. Plus the thing is FCC rules require that you be able to listen to your transmitted signals so you know you're not screwing up the band or what have you. So that will require some modification of the receiver, and otherwise it will not in any way affect its overall performance. So it's just a matter of procedure. Try to use all original materials and don't do any mechanical alterations. One mechanical alteration eventually will be to replace this three conductor phone jack with a 7-pin AN connector, so it's easier to control the circuitry inside the radio as a self-contained unit and not requiring the external accessories that come with this. Like the control box is, if this thing just operates standalone, then I have to have enough pins coming out of here that I can have something like that to control it with. Okay, well that's that.